Tonight we have Stephen and Luke. They're from Comp 3, and what they're going to be talking to you today about is the product called Augie. And so, video analytics tool, very cool, and we'll hear a little bit about the internals. So Luke is a cognitive engineer there. He is working primarily on getting data and the pipeline set up. He used to be in healthcare and has now made the transition to working more generally on these AI type problems. Then we have Stephen. Stephen is also a cognitive engineer at Comp 3. He got his PhD at the University of Michigan in applied mathematics. And now he is working on image analysis and NLP type capabilities. All right, so without further ado, let's turn it over to Luke to get started.
Hey everybody. So like Jason said, we're going to be talking about Augie, this video analytics platform. So what we noticed at Comp 3, or the thing that we were thinking about, is organizations across all sorts of different industries have a lot of video content. People are recording things more and more, and that's something that's just always growing. So organizations have content, they tend to store it, they don't tend to derive a lot of value out of it. There's potential for value in video and audio content, but it's difficult to get at. You need to know exactly where it is and how to categorize it and how to search for it. So the main thing that we're thinking we can do is we can surface undiscoverable content, or previously undiscoverable content. So we're creating this framework to enrich video content, tag it up with the things we find in it, and make that searchable in a sensible format. So that's Augie. So Augie is this framework. It's kind of a collection of tools and a pipeline process that we've devised. And that's really running on text. So that's text from audio transcripts from video. You could have text that is just audio turned into text, and in theory even text itself. So that's not really the main force of the tool. So it also in the video realm, we're also running image recognition. So that's for objects and people. So for the rest of the presentation, Stephen's going to give you a bird's eye view on what we're doing with keyword extraction from text, and then object and person recognition from images. I'm going to give you a little demo, and then I'll talk a little bit more about the pipeline. So I'm going to turn it over to Stephen. And then, of course, we'll have questions afterwards.
Thank you, Luke. And thank you to everybody who's here tonight. It's very nice for you to come. So yeah, as Luke mentioned, I want to talk a little bit about how we are leveraging artificial intelligence to glean previously undiscovered information from videos that might be stored in a very large cache. So first I want to quickly talk about just a few use cases here. Some ideas for people in industry who we think might be interested in this kind of product would be people in the media. They, of course, carry a very large corpus of video that could go back potentially even 100 years. Research institutions as well, a lot of times they hold conferences or summer schools. They can run on for a month, and you can have lecturers presenting talks, and all of this may be recorded in video. So how do you discover things like this? And internally, at a lot of companies, conference meetings, notes, that sort of thing, these things can all be video recorded. You may want to know, when did we talk about this particular thing, or make that decision, or who was attending. So these are the kinds of problems that we would like to address over here. I want to talk about what kind of information we can imagine gleaning from video. So just a couple things that we'd like to be able to answer. One of them is who is in the video here. Another one is, well, what is happening inside the video? And finally, maybe trying to combine these two things to surmise, well, what is the video actually about on some level? A sample that I'm showing over here is, well, before I tell you what's happening in this video, let me just tell you who's in it. So this is Ed Murray over here. You may not be able to see the name labeled up above the face here. In case you don't know, Ed Murray is the mayor of Seattle. It's a little bit hard to see anything that's happening in this image, and nothing has been picked out by our system so far. But if you look down here, you see that we're clearly in a tunnel, which is something that a scene recognition system should be able to pick up. So what we can see in this video is that we are in Seattle at some very big event because the mayor's there, and there's a tunnel. And anyone who may be aware, there was recently a tunneling project that was done in Seattle to basically put a freeway underground, and it was done with this very large boring machine, which is what this ends up being here, though not something that I necessarily would recommend. But if you were interested in discovering this kind of information about instances in which you had a very large tunnel in Seattle, well, then this information that we've pulled over here would allow you to discover that kind of a video. So that's the kind of information we can imagine extracting from video. But we also want to try to extract information from audio here. And we can break this down into a couple different components. One of them would be topic modeling for speech transcripts. We could also do sentiment analysis of these transcripts. Another thing that we want to look at is hot language and loud sound heat maps. So these are the kinds of things that can pull you towards interesting or intense moments that occur within the video, which is useful in situations where a video is very long and you need to find the ostensibly interesting parts. And keywords or named entities from transcripts. We see an example over here at the Federal Reserve, which is an organization. So all of these things should give us insights into the content of what may be locked away inside the video, things that we can leverage to answer the kinds of questions I talked about earlier. So anyway, let me jump into the last item in that list of bullets that I mentioned here. Talk about keywords. And why are we interested in keywords? What exactly are they? And how are we using this to extract information about the video? So keywords are somewhat vaguely defined in the NLP world. They're also called named entities, perhaps maybe even more often. What are these? These are people, locations, organizations, these kinds of things, geopolitical entities. And why do we care about these things? Well, because often keywords can tell you what the actual video, or at least the language associated with it, is about, right? So if you consider this example that I have here, probably confirm the North Korean side and its willingness. Is this working? Okay, it's still working? Okay, it sounded like it cut out a little bit. So you can see here that this is clearly has something to do with North Korea, and as such, it may have something to do with geopolitical affairs. So that's important information. Knowing that the term North Korea or North Korean appears within the text could support topic modeling or a topic assignment if you're doing topic modeling. Another use for this word is that you can tag it and index the video against this, so that way the video will come up in a search of videos that have the word North Korea in them. So these are words of high interest for this reason. So then this leads to the question of, well, how do we find keywords, keyword extraction? So in this situation, this is actually a difficult problem, but it's a problem that's been around in the literature for a long time in NLP, and as such, performance has gotten pretty decent on this, but there are still difficulties that are present. So where's a good starting point for us over here? One good starting point is to, of course, just see how free and commonly used extractors work on this problem, and if they are perhaps production quality. So the most popular these days is likely the Natural Language Toolkit, which is a Python library here. And at least on the sample snippet that I showed you guys on the previous slide and also here, Well, we see the output from NLTK. So the entity that we wanted to flag has been broken into two, when in fact they should be combined. North is somewhat oddly titled a geo-sociopolitical group, and Korean is a geopolitical entity. And somehow these seem suboptimal. It's not what I think most would tag this if we could make up our own taxonomy here. So we're looking for something a little bit better. So, what are some ways that we can solve this kind of problem here? So there are some ways that we can try to clean this up a little bit. One thing that we are doing is using a human curated whitelist. So the idea here is that we can quality control the selections that whatever keyword extractor we're using, such as NLTK, we can sort of set this up as a gateway to make sure that decisions made by NLTK are kind of either rejected because they're not of sufficient quality, or we can let them through the gate but artificially change their taxonomy to something more appropriate, such as, in this case, we're choosing ethnicity. However, this does bring two new problems, at least. One of them is that this whitelist can get quite long, and it requires human supervision, which can be very time-consuming. So this is a little bit suboptimal for that reason. And it also doesn't solve the issue of a keyword phrase that is incorrectly split by an LTK, as the previous example shows us. So how do we handle this? So one idea, of course, is to ditch an LTK and build a custom keyword extractor. And this has advantages that I'll get into in a little bit here. But first I want to tell you a little bit about the keyword extractor whose architecture we're emulating right now. This keyword extractor originally appears in a paper from 2011, which is the first paper that applied deep learning to problems in NLTK. And one of the classic problems that they attacked with it was named entity or keyword extraction here. This is just a bird's eye view of the architecture of this neural network. It's just a fully connected two-layer network here. And it works in the following way. So in this example that I have here, the candidate keyword, it may be a keyword, it may not be, in this case it's clearly not, is in red here. It's the letter on. And we have surrounding context keywords, in this case, to the left and to the right within the text. The idea is that you feed these words here into a word-to-vec model, and this creates your input vector. And then you shuttle that through a trained neural network, and then out come probabilities for the associated tags for not only whether or not is it a keyword, but also where within a keyword phrase does the word appear itself. So, not to go into too much detail, but these tags are, inside, is it inside a keyword phrase, beginning, end, or is it by itself, single? Or outside, which is 90% of the time the case, or at least, right? So most words that you see in ordinary text are not going to be keywords, as if they're outside of a keyword phrase. So on should be classified into the outside option here. So this is just a snippet from the article that I mentioned, where they talk a little bit about the network architecture here. So we have this input layer over here where we take all of our words here and we pass them through a lookup table, which sends these words to vectors. So those vectors contain all the features that we're going to feed into the network. Most of it is word-to-vec vector. But we can also add additional features such as capitalization within the word in question. And then we pass it through the various layers over here and then output the result. So there are advantages with going with this approach, in my view, over previous approaches that have been used for keyword extraction in the literature. One big advantage that they really push in this paper, which I think is great, is that this requires very minimal text pre-processing. So as I understand it, when you wanted to develop, entity extractors or keyword extractors before, you would have to pre-process the text considerably beforehand. For example, chunking, finding phrases within the text, and then processing those through and seeing if they were keyword phrases. So we don't have to do that in this. Furthermore, because this input is context-based, it may be possible, and this is work that we want to do in the near future, to take this model and train it not on a fully annotated corpus, but only a partially annotated corpus training data, where in some sense, if the keywords are distinct enough, for example, the President of the United States, every occurrence of that phrase, you could probably safely assume would qualify as a keyword phrase, as opposed to a coincidental alignment of words that didn't have that meaning that you would think when you hear the name of that office. So you can basically just go through and tag the text for all instances in which that sort of thing occurs. So in other words, because this is context-based and it only depends locally on the words that are around it, you don't necessarily have to have a human painstakingly annotate every single thing in a corpus, which is great because most of any training corpus will be non-keywords. You don't need all of these instances necessarily. So this is something that we want to work on. And we think that this is great because we can then tailor our own in-house keyword extractors that are particular to customer needs, their own taxonomy, their own jargon, instead of being constrained by what a keyword extractor that you would otherwise get off the shelf would have you work within. So I want to move now on to sentiment heat maps and briefly talk about this here. So sentiment heat maps are a way of indicating areas within the video that are potentially interesting. Currently, in its present implementation, this is only based on heated language, and in particular a list of heated words that would be familiar to all of us here, I suppose. I won't say them. But we would like to do more with this, of course. So context can depend a lot on whether or not a word is, or whether or not a word is heated can depend a lot on context. So we want to try to leverage other information that may be present within the video. So not just the actual words within the audio, but is the audio very loud? Or you can maybe imagine a video where we weren't interested in how loud people were speaking at each other, but if there was an explosion somewhere. So that would be a spot of high interest within an otherwise possibly quiet video. So this is a tool that we're also building out. I want to wrap up the audio section here by quickly just telling you about some of the challenges and future work that we plan on doing. Some of this I've already mentioned before. Regarding keyword extraction, we want to take our re-implementation of the SINA model that we've developed in-house, and we want to try to adapt that to different taxonomies and see how well we can work on that particular problem and see how flexible this architecture really is for different situations that might arise. And that's very useful because, as I mentioned, different customers can have different needs, and you want to be able to meet those. Something that we haven't worked quite so much on, we've dabbled in it a little bit, and we want to pick this up pretty soon, is topic modeling. There are two different kinds of approaches you can imagine. Supervised, you can imagine somebody in the media saying, we already have topics that you want us to classify articles according to, sports, politics, science, right? But you can also imagine people who do not know what they want to discover, and they're kind of looking to you to find that information for them. So there are different techniques for these different approaches here for all the different scenarios that you can encounter. So that's future work that we're going to do on the audio end. So, where?
Oh, in the previous slide.
Yes.
How do you create training data? I didn't understand. Can you explain it?
For which part? Keyword extraction?
The third bullet there.
Which one?
How would you create training data?
For keyword extraction or topic modeling?
Yeah, keyword extraction.
So for keyword extraction, there's actually an open corpus from Reuters magazine, Reuters newspaper that you can use. And the SINA paper that I was talking about earlier used that corpus to train its model. And so we've redone the same thing. But this, hits up against a challenging problem. If you want to develop a different keyword extractor for different applications, you need different training data. And it would be very time consuming to completely annotate a different training set all on your own in-house. As I understand it, companies do this. Well, I guess I don't know completely what they do internally because they keep that close to themselves. But
can you show with the second slide where you had the network diagram?
Yeah, sure.
How exactly? So Senna is the same paper as Collaborate. Okay.
Yeah.
So how does it do the training? Sorry.
Right. So this is what the training data looks like. Every single word inside of the corpus is tagged with one of these 5 possible tags. So starting from O for outside, you're not inside of a keyword phrase, and then the other symbols here indicate where you land within a keyword phrase, the exception being single, you are the entire phrase, which is one word. So these are the labels, and each word is labeled accordingly within the corpus. And as you can imagine, that would be very time-consuming to do by hand, and you would want to try to avoid that if possible. So we're thinking about ways to avoid doing that. We think that we can adapt the approach that's used in this model here to do that, to semi-automate the generation of the training data, all the tagging, and then train using that information. Okay, so I'd like to move on now to the matter of extracting information from the video itself. So what kind of information do we want to extract from video? We've broken this down into 3 areas that we're looking at right now. The first is object detection, the next is face recognition, and then finally scene recognition. So these are 3 very popular things that you look at when you're dealing with the broader subject of computer vision and image classification. This is an example here from a video that is freely available from YouTube, from the AP archive. And this is the engagement announcement between Prince Harry and Meghan Markle. As you can see here, we've identified their faces using the face recognition system that we have, and we've also identified a few objects such as a suit that's being worn, and there is a woman here. So let me talk just briefly about some of the all of these components and the challenges that we're encountering as we build them into our platform. So object detection is, you know, a very hot topic these days. It's exploded over the last 5 years. So what are we doing here? We are using pre-trained models that are from the TensorFlow detection model soon to bring in a sort of initial baseline capability into our platform. And these are very good at detecting objects that are reasonably interesting to people out there depending on what their application is. For example, stop signs. You can imagine that that's very important for autonomous vehicles. But this does sort of lead to an issue when you integrate it into a video analysis platform like the one that we're developing. The question is, well, what kind of objects do you want to detect? If you use one of these pre-trained models, that list of objects is limited to whatever that model was originally trained on. And you can take those models and take your own training data and, you know, train it to detect whatever other objects you might want, but then you bump into a few other problems, such as what objects do you even want to detect in the first place? So, for example, we're seeing that there's a suit in this picture and a tie in this picture, but you can imagine that if you have a lot of video that involves the news, and in particular politics, you'll see lots of suits and ties. And this may not be the most insightful information. You may not want that cluttering all of the other information that you're pulling out. So you really care about that kind of thing. Also, when you do figure out what a prospective customer is interested in, and those objects aren't already in your pre-trained model, well, what do? You've got to go out and create training data for this. How much training data do you need to create, and how long is that going to take? So these are problems that we're thinking about and that we'll work on in the future. For now, we are using these pre-trained models here to just incorporate this into the platform as it currently is right now. And then another component that we're working with is scene recognition. And scene recognition is kind of interesting. It's basically a, well, reasonably, at least by today's standards, straightforward image classification problem. You're not using bounding boxes, you're not trying to pull things out of an image, you're looking at the whole picture and you're trying to label it according to some list of categories. So to train our model, we're using the famous Places 365 data set, which is a data set on the order of like 1 million, images of different scenes. And the performance of the models that you get when you use this architecture here, wide ResNet, is not that great. So I think that like top 1 accuracy on image classification is like on the order of 50%. So it's not production ready at all. However, there is an easy way to solve this problem. This data set of scenes is massive. However, it also has a very fine classification. To give you an example, the data set distinguishes between hardware stores and candy stores. We don't really care about distinguishing between things like that. The interior of a store is just fine for us. So what we're working on right now is taking that training data and making a much coarser collection of categories for various scenes to fall inside of. And from some of our preliminary work, it looks like we should be able to get the accuracy up to something that is closer to production-ready levels. So this is something that we're messing with right now, and we expect that this will look pretty good. So that is scene recognition. And I'd like to finish out the image video section of this talk here by talking quickly about face recognition and some challenges we've encountered over here on this end. So face recognition is pretty challenging because training your own in-house face recognition system requires many different steps. So it requires face detection. You've got to be able to find the faces. And that's been around, that capability's been around for a pretty long time. However, once you find those faces, you've got to crop them, rescale them, and then once you have a huge bank of training data of millions of faces, then you have to work on a face classification problem to train a good neural network to do the task that you have in mind. But there's actually great news about this here. Face recognition has been largely democratized. You can find face recognition systems that are near production quality for free, online, for free use, for anything. The one that we're using here is dlib face recognition. So using that, I want to talk just for a second about what this does and what a lot of face recognition models do, how they work. So there are actually different tasks that you could train a face recognition system to do. And most of these face recognition systems these days are trained to do a particular task, which is the following. Given 2 faces, determine whether or not they are the face of the same person or not. And why are they trained to do this? Well, there are a couple reasons. One is that there is a benchmark data set called LWF. Is that the acronym? Loose faces, no, LFW. So I think it's like loose faces in the wild, or I forget the exact acronym. The F is for faces and the W is for wild. And this is basically just, what's that?
Labeled faces in the wild.
Labeled faces in the wild. Great, thank you. So this data set is used to evaluate different systems. It's become a benchmark in the literature. And the task that you have on hand in order to get good performance is exactly what I described. Determine whether or not 2 given faces are the same or if they're different. So using that task, you can actually create something here called a face embedding that will help you to make this decision. So the idea of a face embedding is to take a picture of somebody's face and then map it to a 128-dimensional vector in some vector space here, using a neural network. And the way this works is by using a loss function that more or less goes something like this. When your instance of a training data point, you take a triplet of faces, and maybe the face A and face B are of the same person. So you try to map those faces to two vectors that are close to each other in the vector space. By close, I mean small Euclidean distance. And if faces A and C are different, right, then you want to map those to vectors that are far apart. So you use a loss function that forces that result to emerge after training. And that helps you with the classification task. But another reason why face embeddings are great is because this kind of allows you to take what is a very complicated piece of data, which is the raw pixels that convey the information of somebody's face, and send it to just 128 numbers, which makes that much easier to use for things like nearest neighbor search. So what do I mean by that? So you can imagine the application at hand where you don't want to do face classification, figuring out if two faces are the same, but rather figure out if one face in question matches a particular face in the gallery of faces you already have, which is a different question. And one way you can do that is by taking all of these faces that you already understand in your gallery and throwing them down in some vector space, and then your query face landing somewhere in the vector space, and then asking, well, how should we tag the query face vector, and how can you do that? Well, one way you could approach it is k-nearest neighbor search. What face in your gallery is closest? And that's relatively straightforward to do if your vectors are living in some kind of a relatively low-dimensional vector space. That's much easier than sending all of your data through a neural network every time you want an evaluation. So that is advantageous. But this leads to the question of, well, who should we recognize? So this is a really practical question here. You know, there are tons of people in the world, 7 billion. We obviously can't and don't want to be able to recognize everybody, and in fact, who we want to recognize may be customer dependent. You can imagine for the application of private companies who are keeping, you know, tons of video of meetings, you can imagine them wanting to know, well, who was attending these meetings and who said what when, right? So in that case, the faces you want to recognize are their staff, who are generally not going to be famous politicians or celebrities, right? But you could also imagine other people coming to you, maybe people in the media, and they would say, well, yeah, any face recognition system, you should be able to identify, for example, the President of the United States. So how do we, in that latter situation, sort of come up with a good candidate list of names of people that you would want to recognize? So this is kind of an idea that we're playing with, but one of our thoughts recently, and something that we're just experimenting with, is to create a list of people that's probably way, way too big for now, and see, just kind of mess around with it. So my criteria for famous enough to land on a list that we're using really only for testing inside right now is, do you have a Wikipedia biography with the birthday? Because if you have this, you can actually hit up the Wikidata API and pull useful information about that person, such as their occupation, you know, their birthday. You have a link to their Wikipedia page. You can use that for more information if you need to later on. So what kind of people does this pick up? Well, Brad Pitt is a very familiar person to almost anybody, I suppose, anybody who watches movies. So he lands in because, well, his birthday is publicly known and on his Wikipedia page. Our colleague, Rich Skrenta, is famous enough to have a Wikipedia page, which I'm very impressed with, actually. I don't have one yet myself. So this is one of my ambitions, and he's already there. That's great. But his birthday is unfortunately not on the Wikipedia page, so he actually did land in our list, which I checked about a week ago. So, but anyway, this is a way that you can create a very large list. So you have this large list, and for testing purposes right now, we've pulled images of some of the people that appear on this list. For example, the President of the United States would obviously land in there. I'll just very briefly mention that one should be a little bit careful of this, that you use images that are in the Creative Commons, and you don't try to monetize using images just anywhere from online, because there are copyright issues that go with that. So that is a sensitive matter that one needs to be aware of. But at least for just internal testing purposes, to see the quality of our face recognition system that we're using right now in real-world applications, what do we get? And the results were a little bit surprising. As you'll see on the next slide here, I'm kind of introducing what's going to happen. So as I mentioned before, these face recognition systems that you train are really good at the classification task of determining whether or not two faces are the same or different. But we're actually trying to answer a different question, which is, given a very large gallery of faces and a single query face or a probe set of test faces, how good is the system at correctly tagging the face to the right name? And it actually turns out that this is a bit of a weakness at many of these face recognition systems, even today. What do we see here in these graphs? So this is an image from a paper that introduces a new data set called the MegaFace benchmark data set. And what this graphic here is trying to say is the following. So we have some sort of gallery set with a ton of faces in them, but we also have some large probe set of faces that we want to identify with faces inside the gallery set. What's happening here on this scale on the x-axis is that we are throwing in a lot of distractors or extra faces into the gallery, making it bigger and bigger. So that way, when the gallery is very large compared to the set of faces we want to identify correctly, the probe set, you can see here that even in state-of-the-art recognition systems, the accuracy starts to drop off precipitously over time. And that becomes a real problem. So how can we address this problem? I want to motivate one idea for how we're going to work on addressing this problem right now. And that is that we don't have data just about faces, of course, but we've got all kinds of data about the video up to this point. So, for example, we've got information from transcripts. We also have information about other faces that we have seen within the video so far. So the idea that we have that we're starting to work on is the following here. And I'm going to illustrate it with this example here. So this is a video that we've been working with from YouTube in which musicians appear in a sort of holiday video where they're talking about Christmas plans and decorating Christmas cookies. So in the image on the left, this is a musician. Her name is Idina Menzel. She's been correctly tagged as such by our face recognition system. But on the right here, we have Amy Grant, who is also a musician. She's been incorrectly tagged as the apparent Italian model Fanny Cadeo. They look somewhat similar, but I mean, at least I can tell them apart reasonably easily. So this is a false positive that we would like to rid ourselves from. And this is not an exceptional case, but we found that this occurs very frequently, almost half the time, which is pretty disappointing. However, we think that we can make a dent into this problem by making the following consideration here. Instead of simply choosing the top hit, or most likely candidate name for a face that we found, why not just create a list of, let's say, top 10 with appropriate scores such as Euclidean distance between the faces in the vector space into which they're embedded, and try to leverage other information about the names that appear in that list to make what might be the best decision. So, for example, if Idina Menzel has appeared with very high likelihood, and we're tagging her as such, then if Fanny Cadeo and Amy Grant are two top choices for the second face here, it could make sense to choose Amy Grant over Fanny Cadeo because, well, we have another instance of a musician somewhere in this video. Now, I mean, it's not as straightforward as that. We can't, look at any one of these people with 100% certainty and use that as kind of a baseline. It's more an issue of looking at all of your options and then making the decision from there. So in this case, tagging both people in this video as such makes sense because, well, there are lots of musicians that appear in this video. In fact, if you watch the whole video, there are like 8 different musicians that appear in there. So in your face recognition system, if like you've got musicians trending all across the top in your top 1 or 2 choices, then those may be optimal tags. I want to finish by just quickly talking about processing time considerations. So in the use cases that we have in mind, the video cache can be very large. Let's just say, for example, on the order of 40,000. And we're talking about processing frames from these videos. A typical 30-second video at 25 frames per second. If I did arithmetic correctly, it should be about 750 frames. And how long does it take for us to process a single frame? Using our 1080 GPU, it takes about 1 second. So if you do the math on that, it would take about 1 year to process the entire video cache, which is not workable. So we are thinking about ways to get around this problem. One way that we've done this, which has been great and more or less solved the problem, though, boosts in performance would always be welcome beyond this point, is to look specifically at sample keyframes. So keyframes are shots that are selected out from your entire list of frames for a video that indicate high action moments or scene changes, things like that. And these are useful frames to look at because they could indicate that something new is happening as opposed to just looking at every single frame where things generally don't change much frame to frame. So just to point out what that looks like here, in this particular YouTube video here, you'll find that there are 2,650 frames. However, we are using only 10 keyframes to glean information from that video, and we've selected these keyframes using the FFmpeg utility, which will just show you all of the keyframes, but then we prune that list down even further by pulling out keyframes that are regularly spaced between each other, because even if a scene doesn't change very frequently throughout a time stretch, keyframes will still be forced to occur within certain regularly spaced intervals at least. So finding the irregular time deltas between keyframes and only keeping generally keyframes that exhibit that kind of behavior can take this down considerably. So, so that's how we're overcoming that problem in the present moment. So I want to just finish by talking about recapping on some of the challenges we're facing and the future work that we plan to do as we develop this project further. Object detection, the tricky issues are what do we want to detect in the first place? This is customer dependent. And so how do we be flexible for different customer needs? Something else is what kind of benchmarks do we need to hit in order to be at production quality? So for face recognition, we have pretty similar questions, but as I talked about earlier, we do have this sort of gallery problem where you have just a huge gallery of faces, and how do you avoid getting lots of false positives in this situation? How do you leverage other information about the video? And then finally, scalability. So how do we lessen the time it takes to process images and process a large video cache? So this brings us to the end of the segment where we're talking about leveraging artificial intelligence to glean information from video. And now I'm going to hand the microphone off to Luke, and he's going to tell us a little bit about some of the bits that go into making this all work.
Thanks, Steve. Yeah. All right, so now that we've kind of covered what we're doing kind of in the back end, I'm going to give you guys a short demo to just kind of showcase some of those things. So This is just a front end that we use for demos. We've overlaid it on the core of the Augie system. It's a work in progress. It's not a polished product, but it's just something to kind of showcase how this works and what could be done with it. So, right here, this is just in our generic, what we're calling, it's the AP Archive index. So AP Archive has a YouTube channel with, I think, about 400,000 videos on it. We've just grabbed about 44,000 of them randomly, and it's like 4428. So if we want to look for something that we're interested in, I'm just going to go type in SpaceX here and see what we get. We've got 46 results. So each of these videos is out on YouTube, and we're basically just showing you the video on YouTube. What's interesting here is we've got, okay, here's SpaceX. We found that in the title, as you can see. There was also International Space Station. And sorry, SpaceX is in the text transcript as well. There are other identified keywords in this result set here, and so those are going to show. We're showing those over on the left here. And so maybe you want to know more about SpaceX and Mars, or videos where both terms occur. So that narrows us down to 4 here. So this result, and we can see we've got actually a number of phrases that were picked up here. So if I want to know where Mars appears in that video, I'll just click over here, and it's queued up. Basically, the text, the man says the surface of Mars at that point, and there are a bunch of other things that are queued up in the video. So that's kind of just an idea of, we've got the video, we've processed it, and we've collected this metadata, and now we're making this metadata, we're making it, surfacing it in a way that can be used so that it can be found. So we've also got kind of a real-time input of this article text match tool. So if I was a journalist or a researcher, say I've got some chunk of text. In this case, I just snagged the text of an article online. So I'm just going to pop that into the tool. So out of the article, the Augie system processes all that text. That is real time, and that's live. So when I pasted it in, it fires back with any identified keywords based on the whitelist that we're currently running. So that whitelist is basically a generated whitelist with the technology that Stephen was talking about earlier. But we can really have any taxonomy loaded in there. So that could be client specific or industry specific. It doesn't really matter, and we can have as many as we want. In this case, we've just got kind of a basic one of people and places and things that seem like they might be interesting. So I'll go ahead and click on both of those keywords, President and North Korea, and that gives me 45 videos. So these are things that might be relevant to that chunk of text that I was writing. So if I go down here and I grab one that I think might be interesting, here's the video, and then I've got a bunch of other keywords available here. One thing I want to take note of is we've got a bit of a heat map here. This is kind of a work in progress, but it gives you an idea of what this could look like. So there's a potential highlight. Korean Peninsula was divided in 1945. We've got there's been a Cold War style standoff, and provokes, as they did recently, Donald. So these are just chunks of text from the overall transcript, but they're places where something heated or something interested might be taking place. And these will cue you to the spot in the video that they occur in. For a 2-minute video, you might think, well, you just watch the whole video, it's not that big of a deal. But for something hours long, this would immediately key you into the spot in the video where it occurs. So in the case of research or journalism, you can just cut to the chase and say that's where the information is. All right, so this is the text-based. Oh, yeah, go ahead.
Sorry, does it understand the context when you're searching this meta search? Does it understand the context of what is happening?
The context of what is happening in what way?
So, for example, when you search Donald Trump, right? So does it also understand what kind of context does it is it leading us to?
I'm not sure that I understand the question. The text Donald Trump appeared in that whole article text, and that literally the text Donald Trump and North Korea together as a phrase, those were in our whitelist, so those were extracted. I'm not sure if there's an other context that you're looking for. Okay. Anyways, so the other aspect here is what we're doing with the image recognition that Stephen was showing you. So we have a subset of those YouTube videos where we have run the full image recognition process on. And so I think Stephen showed you a snippet or a screenshot with Prince Harry and Meghan Markle. And here we've got that same video, an announcement video. And what you'll notice here is that rather than being recognized in the transcript text, which there is a textual transcript here, each individual person was simply just recognized from the images in the video. So, for instance, there's Kate Middleton. You know, the reporter asks her for comments. And then there's various points in the video. I think the image Stephen showed you is right about here. There's dialogue, but no one ever says anyone's full name. There's him, her, he, she, that kind of thing. So this is just a good example of that image recognition capability. So that's the demo. Oops.
Another question on that?
Sure.
So, for image recognition, may I know what content detection models you are using?
Which?
To recognize any object other than the face?
Okay, yeah, right now we're just doing faces. But we have image data, object data, but we're not surfacing object data in the front end right now. So it's really just for faces. But Stephen, did you want to?
No,
that yeah. No. So we have objects, but we don't have a set of objects that we're allowing the front end to see and to surface to the user. So the Augie system is kind of it's kind of two parts. It's what we're calling the real-time components, and that's everything that's running to back up the front end, which is the demo that I just showed you. And that's your basic web server. Your basic web server. All of our data is being stored in Elasticsearch, and that the data being the metadata that we've collected and created that has to do with this video content. There's the text annotator. That is running in real time because that's that article text feature. So that's bringing in new text and then associating videos with it. And then we've got an image service there too that will that will be able to process content that could be uploaded kind of live or on the fly. This image right here, there could be a video object store. That's not really so much a real-time component. In our case, we have downloaded content. Like anything that you saw in the demo was downloaded from YouTube and then processed, but it's actually being run from YouTube. So it's kind of we need to run over the content at some point, but once we know about it, then we've got the metadata. Some of the technologies here. This slide deck is going to be available in the meetup, so we've got links for everything here. And then, excuse me, the pre-processing pipeline. So this is where, this is really our system. This is the core of Augie, in that we've got code here that we can feed in lists of videos, so it'll go find the videos. Typically we're running off of YouTube or a proprietary API, or even just a disk, or any kind of storage, just anywhere that there's a cache of data. So we do all the various steps. So that's extracting audio out of the video. If we don't already have a transcript, we make our own. So running speech to text against the audio, doing the video frame sampling, so pulling all those keyframes for the face and object detection. And then we've got some microservices that kind of run in the background that the main video processing code calls. Once everything that can be gathered from the video is, we consolidate all that data and then put it into Elasticsearch, and that's really where it becomes surfaceable and searchable. So some of the pre-processing technologies here. There are a number of ways we could do this. So right now, well, when we started, we were using Google Cloud Compute with a GPU to do some of the machine learning models. We have used Amazon S3 for storage. We're currently using Google Cloud Speech in some cases. All these things are kind of optional and possible, and we've just been trying out what fits. And then we've got some of the other software here that we're using for the pre-processing pipeline. Sure, go ahead.
When you process this, I think you're using linear space distribution, right? So that doesn't use any neural net or any framework like TensorFlow. So may not where TensorFlow is used.
Sorry, that's a Stephen question, but.
Right, so no, DLib doesn't use TensorFlow. We're using TensorFlow for the object detection and the scene recognition.
What is DLib?
So
DLib is it's a large library with different
landmarks.
right. So like for example, there's a face recognition model that comes with DLib, and it's got a bunch of other things in it as well.
Oh, it's a database for images.
No, it's a library with trained models
Oh.
that you can call using a Python wrapper.
So, did you notice any lag when you're processing the video with TensorFlow? Did you notice any lag in the video that's being processed, the frame?
Right. Well,
Is it real time?
no, the processing is not in real time. It takes about a second per frame to process. So, right. Yeah.
Yeah, so, and that's a step in the pre-processing pipeline here, and that's why it is called pre-processing. So every video that we have for any given list of videos, whether that's 5 or 10, or say that whole 44,000 that were in the demo, all these steps run, and then the data gets into Elasticsearch, and then it's available. So we can add in real time, but it's not like you would turn this loose in real time on a video and get the results back right away. We would say, okay, here's the list to process. Once processing is done, now we have all this enrichment available. So, and then, where the magic happens here. So, we did try out a number of cloud solutions, and both Google and Amazon really have viable options there. For us, it was the most expedient thing was just to get a system with a good GPU in-house. And as you can see, we've done this on really simple commodity hardware. That works really well too. So in this case, we've got this gaming rig, and that's the 1080 that Stephen was referencing earlier. So there's kind of a challenge that we figured out with our pre-processing workflow. We'll get to that in a moment. But just as an overall from the prior image, we're doing the downloading. Python manages scripts to manage just the basic callouts. We're using Docker for microservices. That's the text annotator and the image classifier service. So those just interact via REST web services as the scripts run. We've broken out really every even sub-process in this pipeline. We've got them set up so they each operate individually and they can each be run individually. And for a large cache, like in the case of the 44,000 videos, that's been a real help. So any one of us could iterate on one small portion and just rerun that small portion without having to redo any work. So we've got a good system there. And that was one of the initial real challenges is how do we run this at a larger, an ever-growing scale, but have truly pluggable pieces. And then I've got orchestration with override flags, so we can target. Basically, we started writing code so that we could target every piece of code that we wrote, and that's been really, really helpful. So as we grow and as we add more and more and more capability, we can still just run the different pieces anytime they need to be, or anytime they need to be changed.
So how do you version the model? Once you develop the model, do you version it, or how do you handle it?
You mean the recognition models, or? I think we've got those committed. That's Stephen?
Yeah.
Yeah, I mean.
How do you what?
Version the model, do you store it somewhere, different versions?
Oh, how do we version the model? Yeah, so we keep a library of different models that we want to use, and we could run an image through any one of the models that we specify in the Python script. So that's currently the way we're doing it.
So your math models are implemented in the C++ D line.
Yeah, so we just call that as a package. And that's only for the face recognition component, for the object detection, for the scene recognition. Those are.
That's because you're not doing any deep learning neural network.
We're not doing that part ourselves. We're only doing that for the scene recognition.
Because it only has things like SVM and daylight only has.
No, it is a trained deep neural network. But so what you're getting with it is the ability to map faces to vectors. Right? So we're not doing any of the training ourselves.
All right, so we've just got some challenges here. I mostly went over the issue of iterating over an ever-growing cache of videos. So tens of thousands up to hundreds of thousands, how are we gonna deal with that? And just starting out with a system that could be run kind of where each piece can be run independently of the other pieces, that's really allowed us to do that. We've got a fairly simple file system-based cache system. This could be done in databases or other systems like that, but it was so simple for us to just drop each kind of logical video object into its own folder. Every process just generates a file. Every dependent process just reads the file that was generated before, and that's scaled out really well. Another challenge is that we know that there are many clients out there that would have a hard requirement to have completely on-prem systems with no internet access and therefore no call-outs to cloud services. And that's probably, in confidential, like government sector, and certainly anything dealing with healthcare data where they're HIPAA compliant. So right now we do, we use Amazon S3 in the case where we need to actually store or host a video, and we use Google Speech to Text from the Google Cloud Speech Service anytime we need to create or generate a transcript for a video that doesn't already have a transcript. Obviously disk storage or just on-site storage would work for hosting things, and Nuance Dragon actually has some speech-to-text services that can be used as like an internal API call rather than going outside. So that's basically it. Any more questions or thoughts, suggestions, etc.?
if you had a parallel neural network that was filtering people based on something like hair color, would that shrink the gallery enough that it would be accurate? Or would that gallery
Maybe you could go up to
Yeah.
the microphone and then
There you go.
speakers could repeat the question so the microphone would be helpful.
So the question asked was, can we use sort of coarser features of a given face, such as hair color, to shrink the size of the gallery and therefore improve the task of tagging the correct name to the query face? And the answer is, yeah, that is an approach that you could take, and you can use neural networks that are trained to recognize, features of faces, such as whether or not the face is smiling, or, as you mentioned, hair color. My impression is that this wouldn't shrink a large gallery far enough. So, for example, at least for hair in particular, I suspect that that would not work, and the reason why is because usually the faces are cropped out in such a way that you can't really see the hair. But if you talked about maybe other features that can be distinctive, yeah, this is potentially an idea that you could use, but I suspect that it wouldn't shrink the gallery quite far enough. At least specifically with the hair, even if we did pretend that hair was something that was used and the face wasn't cropped away from the hair, you could see in that example that both people were brunettes, and still we have this tagging problem that happens over and over again. So it is something that we're thinking about. Any other questions?
Can you elaborate on shrinking the 2650 frames to 10?
Sorry, can you say that again?
In one of the slides, you mentioned you had taken a video with 2650 frames and then you shrink it down to 10 frames.
Oh, yeah, sure, the keyframe. Right, so let me very quickly talk about what we're doing here. So that was over here. Right, so the point that I was making here was that if you processed all of the frames in a video, which would be way overkill, then you would end up spending way too long going through a video cache that a prospective customer could give to you, which is clearly problematic. And perhaps the most obvious way that you can attack this problem is by noticing the clear fact that most adjacent frames don't contain different information from each other. They don't change very much frame to frame. However, keyframes that are often indicators of change, such as scene changes within a video or high motion, that sort of thing, are therefore good places to look at because they can indicate locations where the content of the video has changed substantially, and therefore we should analyze them. Now, we're not looking at all keyframes. We're kind of playing with the question of how many keyframes we should actually look at. In this particular instance, we got away with 10 keyframes, but we have seen some instances where our sort of purge down to X number of keyframes was too much, and we lost some information that we otherwise would have wanted to gain. So the right way to answer that question is still something that we're working on. Let me elaborate a little bit on the phrase irregularly spaced. I can't remember if I mentioned this before, but as I understand it, keyframes may occur in locations where you have high motion or scene changes, things like that, where a lot of pixel values can change. But they can also occur regularly after some predetermined time gap. And so you don't necessarily want to keep keyframes that keep on recurring after X number of frames have gone by, because they may not be indicative of change and therefore new content. So we do sort of a second stage purge down from all frames to keyframes, and then keyframes that seem to not occur at regular intervals, to at least get down to 10 keyframes in this example. And sometimes that last purge level is too much, so where we should land in between is still something that we're working out. Are there any more questions?
So,
Yeah.
So how do we fetch
let's say you have two frames, then you are going to compare the similarity or just a pixel computation, whether if we can see the significant changes in the pixel difference, then we can consider these two as two different keyframes.
Right, so right now we're only looking at the amount of time between the keyframes. So what we do is we look at all of the keyframes pulled out with the FFmpeg utility. And when we have that list of all of those time markers, we go through the whole list and we sample the different intervals throughout. And when we see certain intervals occur often, like above, let's say 60%, then we infer that that is sort of the regular interval at which you will space keyframes if there aren't significant events happening, such as scene changes. And then we purge those keyframes that happen at the endpoints of those intervals out, or at least the right endpoint, and we keep those that are at the right endpoint of irregular intervals for now. And as I mentioned before, this usually works, but sometimes this can be too harsh and pull out keyframes that you would otherwise want to include. So it's kind of a trade-off, and there are smart ways that you can do that we're thinking about right now and trying to work on. Are there any more questions? I'm sorry, can you say it louder? And
Is your solution available for us to try out?
Is our solution what? Available to try. To my knowledge, it's not publicly available yet. Maybe, yeah.
Yeah, so we can share our email with you, and if you're interested in a demonstration or getting further with it, just get in touch with us and we can figure that out. There isn't anything public facing or publicly available at this time.